All right, so now we're going to learn about valence electrons and atomic ions. We talked a little bit about ions before. Now we're going to be able to look at the periodic table and figure out the type of ion that an element wants to form. And it has everything to do with this idea of valence electrons. So let's talk about that real quick. Valence electrons are the outermost electrons, meaning they're the highest energy, they're the easiest to remove. It turns out that the way that the periodic table is organized is that every element that's in the same column has the same number of valence electrons, okay? Again, the outermost electrons. So let's just take two simple examples and sort of see here. Remember that hydrogen is the simplest atom. It has one proton surrounded by one electron. Lithium has three electrons. If we drew out the electron configuration, it would be 1s2, 2s1. So that principal quantum number corresponds to the valence electron shell. So if I'm thinking about that again as the outermost, and I'm going to draw my lithium atom, I have three protons in the middle. Now I have two in this 1s layer, and now one in my outermost or my valence shell. Okay, and we could draw the same thing with nitrogen. It has one 3s electron. Potassium has one 4s electron. Okay, everything in that first column has one valence electrons. And again, that's the number of electrons corresponding to that highest principal quantum number in the electron configuration, okay? So let's just sort of zoom in real quick. Again, in terms of the highest principal quantum number for, let's look at these guys here. For oxygen, it's 2, and it has two 2s electrons and four 2p electrons for a total of 6 valence electrons. Likewise, sulfur, even though it has a higher principal quantum number of 3, it still has 6 valence electrons because it has 2 3s and 4 3p. Okay, so this is this concept of whatever your highest energy or what we kind of think of as outermost electrons, the number. Again, it falls on the periodic table. So this column has one valence electron. This column has 2 valence electrons. This column has 3, 4, 5, 6, 7, and this column has 8 with the exception of helium, which is really teeny tiny and only has 2. Okay, everybody else in that column has 8 valence electrons. Okay, and again, it's if you wrote out the electron configuration for any one of these and then just focused on whatever the highest principal quantum number is and counted those electrons, those are the valence electrons. Okay, the reason why the periodic table was actually organized before anything about valence electrons was known, because they were grouped in columns by how reactive they were in terms of, did they undergo the same type of reactions? So it turns out that oxygen and sulfur undergo very similar type of reactions. And we know now that's because they have the same number of valence electrons. So we say the number of valence electrons an element has gives it a certain personality, right? They tend to react in very similar ways. And we'll see one example of that here. Okay, so before we jump on to ion formation, there's another thing we have to know, which is how to draw Lewis dot symbols for our various elements. These are just very simple kind of drawings where we're going to take, so for example, carbon, we have the atomic symbol C. And then we're going to represent the valence electrons around this symbol as dots. So let's just go back real quick. How many valence electrons does carbon have? It's got 2 electrons in an s orbital and 2 electrons in a p orbital for a total of 4 valence electrons. So that means that the dot structure for carbon would have 4 all around it. Okay. If it had 3, let's do a simpler example, something like beryllium, which has 2 valence electrons. So that's this guy here, has 2 valence electrons. We tend to put them on opposite sides. Really, it doesn't matter as long as you follow this rule here, which is you don't put a second dot in the same position until everything has a dot in a single position, okay? So again, this would be carbon, so it has 4. What if I go one more and have 5? So for example, nitrogen will have 5. I write my symbol for nitrogen. I go around 1, 2, 3, 4, and then I can double up on one side. Okay? And again, because every element within a column has the same number of valence electrons, they'll also have basically the same Lewis dot symbols with the exception of the letters in the middle. But right, so this column, again, let's just go through a number. 1 valence electron, 2 valence electron, 3, 4, 5, 6, 7, 8. And notice that that indeed corresponds to the number of dots in each column. So oxygen has 2, 4, 5, 6. Sulfur, 2, 4, 5, 6. Selenium, 2, 4, 5, 6, etc. I will note that, notice how when we did this counting, we sort of skipped over, whoops, let's get rid of this. We're skipping over this transition block here. Okay, so if I was looking at a full periodic, things just get a little complicated there. It's a little bit beyond this course. But if I was looking at my periodic table and I wanted to assign the number of valence electrons, I would start from the left, 1, 2, and then I would jump over the transition metals, 3, 4, 5, 6, 7, 8. Okay, and again, with that exception of helium, which has 2. All right, and again, and let's note, you can sort of see here, helium has 2. But now our Nobel gases all have 8, 2, 4, 6, 8, all the way down the line. Okay, it turns out that this is kind of the key to ion formation. Elements want to have 8 valence electrons. Okay, so fluorine currently has 7. It really wants 1 more to make it 8. Okay, all the elements want to become Nobel gases, basically. You can think about the Nobel gases as the popular kids that everybody wants to emulate. Likewise, if we were to take sodium, you'd have to give it 7 electrons in order to get to the Nobel gas configuration. So actually the easiest thing the easiest route to get there would be the opposite. It'd be to get rid of that electron. And then it would have a full valence shell, just 1 layer down. Okay, so turns out that this half of the periodic table likes to accept electrons in order to get to the Nobel gas configuration, whereas this half of the periodic table, they'll give up electrons in order to get to a Nobel gas configuration. This has a lot of implications in terms of the ions that these elements form. So if you remember, we talked about ions a little bit. We went over the nomenclature. If an atom loses 1 or more electrons, it becomes positively charged and is thus a cation. Remember, cations are positive. And the other thing an element can do is it can gain electrons, become negatively charged, and be an anion. Okay, so just going back over here, these elements will lose electrons and thus become cations. These elements will gain electrons and thus become anions. All right. And we can see just how many they're going to gain or lose based on how many valence electrons they have. So calcium, and let's just sort of pick this out on our periodic table. Here's calcium over here. Again, we're going to ignore these transition metals. Calcium currently has how many valence electrons? Hopefully you can tell by looking at the periodic table. 2. Which means in order to get to a noble gas configuration, it would have to lose 2 electrons, right? And so that's what this is showing here. Is even we can even use our noble gas abbreviation for calcium. We would write argon and then 4s2. Well, if it loses those 2 4s electrons, it would have the same configuration as argon. And again, that's every element's dream, is to become a noble gas. So in terms of how many electrons it has to lose, it has 2 valence electrons. It would have to get rid of both of them, right? So the atomic number for calcium is 20. So neutral calcium has 20 protons and 20 electrons. If it lost 2 valence electrons, it would have 20 protons, but now only 18 electrons, giving it a charge of +2. So calcium likes to form +2 charged ions. It doesn't form +1, it doesn't form +3. If you have a calcium ion, it's always got a +2 charge. Likewise, let's do another example. Let's do fluorine. Okay. Fluorine has 9 protons and 9 electrons. How could it get to a noble gas configuration the easiest? It can gain another electron. That would keep it at 9 protons, of course, because that's what makes fluorine fluorine, but then give it a 10 electrons for a total charge of -1. So just like calcium always forms +2 ions, fluorine always forms -1 ions. Okay. And then it's not too hard to sort of figure out. So again, this is our periodic table: 1 valence electron, 2, 3, 4, 5, 6, 7, 8. It's not that hard to figure out that everybody in this column here is in the same situation as calcium. They all want to get rid of 2 electrons in order to get to a noble gas configuration, which means that they all form ions with a +2 charge. Okay. Lithium, you know, these first column elements here want to get rid of 1 electron in order to form a noble gas configuration. So they form +1 ions. All right. We can look on the other side of the, well, and then notice aluminum's got 3 valence electrons. It will get rid of all 3 and form a +3 ion. Notice how we're kind of glossing over what happens down here. Things, they follow the rule pretty well, but they can get a little complicated. So we're going to focus on the major ones here. All right, likewise, let's look over at fluorine again. It wants to gain an electron to get to that noble gas configuration. Well, so does chlorine, so does bromine, so does iodine. All of them have 7 electrons in their valence shell. they would take one more to get to 8. All right, what about oxygen? It has 6 valence electrons. How many would it have to gain in order to get to 8? It would have to gain 2, which would give it a charge of -2. So everything in this column would, when it's ionized, will have a charge of -2. And then lastly, nitrogen has 5. How many electrons would it gain to get to 8? That would be 3. Okay, so you see, based on where they live on the periodic table, based on the column that they live in on the periodic table, we know the type of ion that they want to form. Okay, so let's do a few here. Sodium, calcium, oxygen. Sodium lives in column 1, so it has 1 valence electron. What's the charge going to be if it gets ionized? Just like everything in this column, it will be +1. Oxygen currently has 6 valence electrons. How does it get to 8? Could either get rid of 6, but that's going to be really hard. The easier thing would be to accept 2, and thus, just like everything else in this column, will contain a charge of -2 when ionized. I don't remember what the third one was. Calcium. Oh, we did calcium, but nonetheless. Calcium has 2 valence electrons. What's the easiest way to get to a Nobel gas configuration? It's to lose both of those valence electrons. So that takes us to a charge of +2. Okay? And we can represent this with our Lewis dot symbols as well. So so let's just say sodium originally had a Lewis dot symbol of just the 1 dot because it had 1 valence electrons. We can actually sort of convince ourselves of this going back to this table here. Sodium has that 1 dot. Chlorine, because of where it is on the periodic table, let's actually just look here, is right here. So it should have 7 dots. Oh, that's the wrong slide, sorry. One, 2, 3, 4, 5, 6, 7. But then as we talked about, how does sodium get to its Nobel gas configuration? It gets rid of that valence electron, right? So the valence dot symbol for this ion would just be sodium without that dot and a positive charge. Likewise, chlorine would accept an electron. So I'm going to draw in that 8th dot. Notice how now it has a full valence shell, a full octet, as we call it, because there's 8 of them. And then it would need a negative symbol. We do tend to put it in square brackets, but it's not the most important thing in the world. Okay. But yeah, so both of these atoms now have full valence shells. Sodium's sort of emptied down to what would be the next level. Chlorine's accepted an electron, but these are how we would draw the Lewis dot symbol for these ions. Okay, so now we're going to do one last problem where we do the Lewis dot structure for the neutral atom and the ion. So we have selenium, phosphorus, selenium, and strontium. So what we're going to do is, again, find these on the periodic table. What was the first one? Phosphorus. So let's draw the element form of phosphorus. We're just going to put a dot for every valence electron it has. Let's actually do this whole thing from scratch. if I wanted to figure out how many valence electrons phosphorus had, I would just start counting columns. So 1, 2, jump the transition metals, 3, 4, 5. So I would go ahead and put 1, 2, 3, 4, 5 dots on the outside of phosphorus. And then if it wanted to get to 8 to form what would be called the phosphide ion, how many electrons would we need to add? Right, so we would need to add 1, 2, 3 in order to get to our 8. So this would be now a full octet, which is what we wanted, with a charge of -3. Oops. And again, it's -3 because when it was neutral, it had 5. So this one's new. Oops, I guess it's actually, this one's new, this one's new, and this one's new, right? So now I have 3 more electrons than I did protons, which is why the phosphorus ion would have a charge of -3. We'll do one more of these and then leave the other one for you guys to check yourself. Let's do selenium. Again, we'll do it from scratch. Here's selenium. So if I'm going to draw its Lewis dot symbol as a neutral atom, I'm again going to figure out how many valence electrons it has. 1, 2, 3, 4, 5, 6. So 1, 2, 4, 5, 6. And then how many electrons would it need to accept to get to that full octet to become a Nobel gas, so to speak? I would need to go 1, 2 more electrons in order to get into that Nobel gas. So that means a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. And again, that would have a charge of -2. And again, that's because this electron and this electron have been added. Okay? So one of the things you can do sort of just when you get a periodic table in front of you on an exam, for example, is to just go through and quickly put in what the charge would be on those ions. So this would be +1, this would be +2. Again, skip the transition metals, this would be +3. For going the other way, remember, we're not going to put any number on the Nobel gases because that's what everybody wants to be. That's why people gain atoms gain or lose electrons. But fluorine would have a charge of -1, or rather the halogens, everything in that column. The oxygen column, a charge of -2, and the nitrogen column, a charge of -3. So you could put those numbers in, and this is kind of like your cheat sheet, so you know, oh, what does bromine form? That -1 charge, okay? But you can figure out the type of ion that an element forms just by looking at the periodic table. All right, one thing I do want to say is I originally had recorded the periodic trends lecture before this one. And the way that I'm going to arrange it, I think it makes much more sense to discuss this before discussing periodic trends. So you'll hear me refer in the periodic trends lecture to being like, this will make more sense in the next lecture. This will make more sense in the next lecture. I'm talking about this one that you're watching right now.